Hi everyone. I just wanted to correct a few things that I discussed about sectoring and the number of interferers. So I've more or less completed the cellular concept. As I discussed, I didn't cover about, there are few things which I left out called zoning, micro zoning and cell splitting. I didn't go in much detail, very briefly I discussed, but this is sufficient. Whatever we have discussed so far in cellular concept is sufficient. I won't test you more than that. Okay, but understanding the concept is very important. Why do we go for cell splitting? I mean, what the first fundamental concept of frequency reuse enables, so those things has to, I mean, enables to have more number of users with a finite number of channels. So that's the idea, and those things should be clear. The next question was, we also discussed what was the advantage of going for so what was the advantage of going for clustering. So we said ideally the best way, we said, we derived an expression and we said that the user capacity, S is the number of channels, L is the the total number of cells in a given region. So usually what happens is, once, let's say you decide upon a geographical area and you want to cover a geographical area with uniform distribution of population, let's assume that, then what you will normally do is that every base station requires a certain amount of investment. So there is a financial investment, money, it costs money. So you will decide upon a certain number of base stations and you will divide this region into several cells, each of same radius. Let's assume the population is uniformly distributed, and so we are going to distribute it, we will just going to have L number of antennas. We will decide L number of base stations. So L base stations will have a certain money investment. Okay, so then once we have these L base stations, then we decide what is the power the base station has to radiate. Okay, what is the power the base station has to radiate? That gets determined by the mobile phones. So the handset will have its own noise levels and all that, sensitivity. We discussed something called sensitivity. Based on that and the cell radius, we decide what is the cell radius will more or less gets fixed once we decide the number of number of cells in a given region. Okay, so these things we can decide based on the handset, what is the power you are ready to radiate, how many antennas you are ready, how many base stations we are ready to invest money on, all that. Once we decide, we are going to fix the radius, the number of cells is fixed. The next step is clustering. How many clusters should I go for? Okay, so ideally the maximum number of clusters will be limited by S here, because you should give at least one channel per cluster per cell. That's the fundamental limit. So we can get limited by that. The cluster size can be as high as the number of channels itself. Minimum value of the cluster size can be 1. So we can see that if I want maximum user capacity, then of course your cluster size can be n equal to 1. But we also discussed cluster size and carrier to interference ratio are directly related to each other. So as you reduce your cluster size, your carrier to interference ratio also reduces. So once I fix C by I, or I'm going to call it as CIR, carrier to interference ratio, or I might also refer to as SIR, signal to interference ratio. Once I fix it to a certain value, okay, you should ensure that this number, which is your CIR, this should always be greater than or equal to a CIR, some fixed value. I'll call it norm, as the nominal CIR which you are supposed to meet. Okay, so then this puts an upper limit, lower limit on the value of n you can go for. Okay, so the number of cells you can go for has a lower limit based on what is the interference ratio you need. Now let's say you need more clusters, at the same time you want to get away with a lower interference, then that's when you go for sectoring. Okay, so I discussed in the lecture and even in your textbook that what they generally give is that when you have any given region, we start with 120 degree radiating antennas. Antennas will have a radiation pattern. So usually we mention it in a two-dimensional plot. So an antenna, so this is the circular plot where the antenna is at the center, okay, located at the center. This is the point where the radiation happens, from where the radiation starts. Now in antennas we define what we call as beam width. So a beam width antenna radiation pattern may look like a bell like this. Okay, so this angular point is what we refer to as beam width. Theta is what we call as the beam width. Now the beam width can be measured in angles, in radians. it can be measured in degrees. So for example, we can have a 60-degree antenna, radiating antenna. So which means if I assume this is 0 degrees, so it will radiate in the angle of plus minus 30, or it can radiate for 120. So in that case, it will radiate between plus minus 60. Okay, so the beam width is going to be 120 degrees or 60 degrees. It can vary. So which is what we are going to choose here, and we'll have sectored antennas which can radiate in a certain beam width. Okay, beam width is BW. I'll probably set a set of questions for your next week. I'll probably give you an assignment which will contain questions which you have to solve, so that I'll also ensure that you are watching the videos. Okay, so you may have to answer that questions and then write back to me in an email. I mean, the same group. I'll mail you the instructions. Okay, yeah. So now I discussed in the class that generally when you go for 120-degree sectoring, the number of interferers reduce from 6 to 2, just 2. It reduces from 3 to just 2. Almost there is a 1/3 reduction. 1/3 translates to 10 log of 1 by 3 is your reduction in your carrier. That's your reduction in your carrier to interference. Rather I would say an increase in the carrier to interference ratio, reduction in the interference power. I can say the interferer power reduces, so it's your carrier power or signal power PS by PI. So your PI now becomes PI by 3. Okay, so in logarithms, if I can express it, it will be 10 log 1 by 3, or I can also express these units as 10 log 3 as reduction. Okay, so that will be your reduction in your interference power, so your carrier to interference ratio increases. So then I can go for a smaller cluster size and do sectoring and get away with the problem of going for a higher cluster size. So the problem was that the problem of going for a smaller cluster size was more interference. I can reduce interference by choosing a smaller cluster in combination with sectoring. So I'll give a problem. You will slowly on one of the questions in the assignments which I'll be mailing you by this week. Okay, so where you can see how all these 3 parameters can be played around with. So the cluster size, number of channels per cluster, and sectoring. Once you do all the 3, you will see and I'll ask you to use your the Erlang charts to compute your traffic. Okay, and if your traffic is high, then you can support more users. So that's what it means. So I'll ask you to compute that and see for different cases. Then you'll understand how all these parameters play around. Okay, how could we play around with all these parameters? So the main point I want to discuss in this lecture is that I discussed the number of interferers is 2 as we reduce from when we go for a sectored 120-degree sectored antenna, it reduces to 2. And I said that in a specific case when you are on the cell edge, so because this antenna will radiate in this region, so when you are in this point or this point, anywhere along this edge, you can receive 3 interferers. Okay, but I said this is generally we ignore this. That's what most of the textbook, the analysis, they assume that we ignore the cell edge. Okay, cell edge is ignored, so we don't really worry about the radiation pattern from the cell edge. Okay, so then it will be just 2. So this guy contributes to this, and this guy also contributes to the radiation. So we are interested in this region. If you see, both the blue and green radiate in this region. Okay, but I said that this cannot be generalized. This is not a generalized result where I can say there will be only 2. The number of interferers is a function of the cluster size as well. So which is what I wanted to discuss in this class. So very quickly, I want to show it for n equal to 4 here. So I've chosen n equal to 4, the radiation patterns for this, and I've shown, so for example, n equal to 4, it should be clear now. So I've picked 1, 2, 3, 4. So this is a cluster. So the cluster is like this. So this is your cluster. The 4 cells form a cluster, and I just repeated that, tessellated it to generate this entire region. Okay, so now to get an n equal to 4 cluster, I square should be equal to 4 or I equal to 2. So I equal to 2 and j equal to 0, or I equal to 0 and j equal to 2. Both of them will work. Okay, so you can use that. So you can see that the co-channel interferer will be 2 units away from the any one of the cell centers. You want to go to any co-channel interferer, you have to travel 2 units. Okay, so that's the way this n equal to 4 cell structure is built, cluster is built. Now if you see this n equal to 4 cluster, in this we want to find, assuming a 120 degree sectoring, you can see there are only two interferers here. In fact, the others don't even touch the region at all. They don't even touch the region anywhere within the cell. Even the edges they don't touch. If you see for n equal to 7, they were actually touching the edges. Okay, so I'm going to generalize this and say for any n that is of the form I square or j square, I mean it doesn't matter, where I is a finite number k and j is 0. Okay, you can either have j equal to k and I equal to 0 or anything. If n is of this form, a square form, then you can assume the radiation pattern will be the number of interferers will be 2. Why I am saying that is that the other clusters, it's going to move in this direction. The other, let's assume any n equal to I square kind of clusters, your interferers, you have to move only in this direction to find the next interferer. Okay, so since we can extend the same thing and say that as the cells move farther and farther away, the radiating patterns will also move farther and farther away from this. So obviously these 4 will not contribute at all. So only 2 will be contributed. So we can say that for n equal to I square, this result will hold perfectly true. Even on cell edges, you will not see any radiations other than 2 interfering wave stations. Okay, so you can very quickly verify for 60 degree radiation. So I can pick one pattern here. So I'll pick this cell. So I'm showing it here. So if let's say if I pick this cell here, so this is the 60 degree radiation pattern. So again, when I go for 60 degree radiation pattern, so you should be worried about this region, because this is the region where you are concerned. Okay, so in the 60 degree radiation pattern, so now you can see this anyways obviously fully radiates in that region, and you will see that every other cell doesn't radiate. So the number of interferers just comes down from 6 to 1. So another 3 dB improvement from going from 120 degrees to 120 degrees to 60 degree sectoring. Okay, the antenna beam width reduces to 60 degrees. So the number of interferers just reduced to 1 here. Okay, so now I'll take another example. So I wanted to explain that this is easier to understand, n equal to I square case. So where obviously it is 2 for 60 degrees, for 2 for 120 degrees, and 1. I'll call I naught as the interferer number. I naught equals 1 for your beam width. BW is your beam width for 60 degrees, and your for beam width of 120 degrees, your I naught will be equal to 2. This is for n equals of the form n equal to I square. Okay, I haven't shown for n equal to 1, when we should understand that this holds true for 1 equal to 1 too. So let me quickly, for the time being, you can ignore the numbering here. Okay, so then if you see for n equal to 1, n equal to 1, that's also a square number. So if you see every cell, every neighboring cell will be an interferer. So the radiation pattern, if you see, only 2 of them will contribute. So this guy is going to radiate in this. See, we should be interested in this region. Okay, and this guy is also going to radiate in that region. So you will have 2 interferers even for n equal to 1. The other 2, for example, this is going to graze it at the edge, and this guy is also going to graze it at the edge. So these 2 we can ignore. Okay, so because it's on the edge, we'll ignore it for the time being. So we can say for 60 degrees, if you have n equals I square, that holds true for even 1, 2, 4 and so on. No, not 2, I'm sorry, n2 is not possible. So 1, 4, 9 and so on. All the squares, this relationship perfectly holds. For a beam width of 60 degrees, for a 60 degree sectoring, there will be only 1 interferer. Okay, and again we discussed this as well. So since it is 120 degrees, 360 by 3, okay, and 60 is 360 by 6, so you get just 1. The number of interferers reduced by 1. So you can look at it that way as well, only for n square cases, where it's perfectly you have to move on the sides and you reach the interferers. Okay, on all the sides. Now the next case is I've taken a case of 3, n equal to 3, and you can see here we will be having 3 interferers for 120 degree sector radiation. Okay, for 120 degree sectoring, you will actually have 3. So I have taken a cell, n equal to 3 is also a possible number. 1, 1 will give you n equal to 3. If I assume I as 1 and j as 1, then you get n as 3, and so that's also a possible cluster. And you can see I've written here this forms a cluster 1 2 3 here. So again 1 2 3 1 2 3 and so on. The nearest neighbor you have to travel 1 1, so you have to travel a distance of 1 unit in this direction and 1 unit in this direction, and you will reach it. Because we move from cell center to cell center, we'll be traveling 1 here 1 here. This distance will amount to root 3. Okay, root 3 in terms of the distance, so unit distances here. Okay, I'm sorry. So this distance from center to center, the distance is going to be r, and r. So that's going to be 3r, and we know r is d by root 3. So it will be root 3. So that's what I meant. Root 3 in terms of d. Okay. Okay. So now if you see n equal to 3 for that cluster, if you see you will actually have, so this is the region I am interested in, where the radiation can take place. Where the EM radiation is, the interfering radiation can interfere with your mobile signal. So for in that region, if you see, this guy contributes because this is radiating in this region, and this guy will also obviously contribute. This is fully behind it, so it will be fully maximally corrupting. Okay, and this guy also is radiating in that region because this is all a part of its radiation region, radiation zone. Okay, so there will be 3 interferers. So which is why I said it also depends upon the cluster size. We can't ignore the cluster size, so it will depend on the cluster size. And for n equal to 3, we will actually have 2. The interferer, if when I go for 120-degree sectoring, the number of interferers will reduce to 3. From 6 it will come to 3. So you'll only gain by 3 dB as opposed to 4.7 dB in case of n equal to I square kind of clusters. Even n equal to 7 also we gain there. Okay, so that's one thing. So what we observe here is that maximally when you go for 120-degree sectoring, at max you can have 3 interferers, and minimum you will have is 2. So that's all I'm trying to say. Okay, it depends on the geometry and the cluster size. It mainly depends on the cluster size, and the interferers can be ranging from 3 to 2. Okay, and I haven't shown it for n equal to 1, but I've discussed it very briefly in the last lecture and the last slide, so that should also be clear. Okay, so that's it about this. I will very soon upload the problems based on this cellular concept, mainly for you to understand sectoring and the traffic, how to assign channels, and how to compute the cost and all that. So that I'll just give one assignment for you guys to go through that, and you'll have to solve it and return me the answer sheets by mail. You'll have to send it as a PDF file, and I'll write the instructions. So I'll do that before this weekend. Okay, so I'm going to post videos on wireless channel models as well. Very soon I'll do that.